What is a wormhole? The significance of wormholes goes far beyond long-distance transportation. Wormholes may allow us to glimpse the essence of the universe and help us understand what the universe really is. The concept of wormholes was proposed by American physicist John Wheeler, one of my most admired physicists. Some may wonder why Wheeler, who never won a Nobel Prize and isn't particularly well known, is considered a master in the field of physics. The answer is that Wheeler's ideas are breathtaking and world-changing, and he has many of them. As an example, in 1965, physicist Richard Feynman told a story during his Nobel Prize acceptance speech. He said that when he was a PhD student at Princeton, his advisor Wheeler called him one night and said, "Feynman, I know why all electrons are identical. It's because there is only one electron in the universe." Wheeler explained that on the timeline of the universe, an electron travels forward in time, gets hit by a photon at a certain point in time, and then reverses direction. If it gets hit by another photon, it will reverse direction again. The electron's path is like the meandering yellow river. If you take a snapshot at any moment in time, you might think there are many electrons in the universe, around 10.80 electrons in our universe at any given time. Why are there positrons in the universe? It's because half of the electrons are traveling backward in time, showing opposite charge and parity. When electrons and positrons meet, they annihilate each other. Feynman praised Wheeler's explanation and asked, "But if there is only one electron in the universe, shouldn't there be an equal number of electrons and positrons in our world?" Wheeler didn't have an answer and could only say, "Maybe positrons are hiding inside protons." This became Feynman's famous one-electron universe hypothesis. It's difficult to prove or disprove this hypothesis, and physicists today tend to think of electrons as waves in an electron field, rather than particles. But Wheeler's hypothesis was a wild one. According to his theory, what are people? People are knots of particles in space-time, a tangle of particles in the universe. Let me introduce another one of Wheeler's fantastic ideas. We all know the double-slit interference experiment, which creates two extremely narrow slits and allows only one photon to pass through at a time. If we observe the motion of the photon, it will appear in particle form, hitting the backboard one by one. If we do not observe the photon, it will become a wave and produce interference fringes on the backboard. This is the paradoxical nature of the quantum world. Its ultimate form is uncertain and depends on the observer. But Wheeler wondered if it was possible to observe this anomalous phenomenon in the macroscopic world as well. In 1980, astronomers discovered gravitational lensing in the universe. Simply put, a distant celestial body and the Earth are separated by a black hole, acting as a refractive lens, and the light from the distant celestial body is refracted into two images and emitted to the Earth. Wheeler thought that if we use two serial telescopes to receive the two images separately, it is equivalent to the double-slit interference experiment. If someone observes, it is equivalent to observing the motion of the photon. At this time, both telescopes should have images, but if no one observes, one telescope will have an enhanced interstellar image and the other will have none. This indicates that the two images interfere, which means that wave function collapse will occur on a huge cosmic scale, implying that the universe is uncertain. Whether the universe exists depends on our observation of it. This is a brilliant idea. But why wasn't the experiment completed? Because the two light groups refracted by the black hole into the Earth are not the same group of photons. The second group of light arrived 1.1 light years later than the first group. Because these two light groups do not belong to the same group of photons, the experiment cannot be done. This is Wheeler's famous delayed choice experiment of the universe's double slit. Fortunately, this experiment was not completed. If the universe is really illusory, our human worldview may collapse. The universe's delayed choice experiment is especially exciting. The reason why Wheeler is called the master among masters in the physics community is that his thoughts are too active. He is actually a philosopher among scientists, always trying to find the fundamental questions of the universe. Let's go back to 1935. Einstein and his colleague Nathan Rosen jointly published a paper, which is named after their initials ER. In the paper, they believed that a bridge could be formed between two closed space-time celestial bodies called the Einstein-Rosen bridge. Wheeler said that the so-called closed space-time celestial bodies are so massive that even light cannot escape, and these celestial bodies should be called black holes. The name Einstein-Rosen bridge is not intuitive and it should be called a wormhole. Therefore, the names of black holes and wormholes were invented by Wheeler. This is his ability. He can express complicated science in simple and intuitive concepts. Also, in 1935, Einstein, Rosen, and another colleague, Podolsky, published another paper named after their three initials, EPR. The paper stated that when two particles interact, they will produce entangled states, and no matter how far apart these two particles are, even at the two ends of the universe, they will be connected to each other. Einstein did not like this concept. He believed that if quantum entanglement really exists, it means that the interaction between quantum particles is superluminal. He called this kind of interaction a ghostly action at a distance. Continuing from 2013, physicist Juan Maldacena sent a brief email to his friend Susskind with the line, "Ere EPR." Susskind, a renowned physicist, immediately understood the significance, and the two collaborated on a paper proposing that wormholes and quantum entanglement are essentially the same things. In simple terms, two distant quantum particles can exchange information instantaneously because they are connected by a wormhole that we cannot yet fully understand. Information can be transmitted through the wormhole to pass between the quantum particles. This theory led scientists to boldly propose in 2020 that wormholes are macroscopic entanglement, and entanglement is microscopic wormholes. Under this theory, scientists began working to create the first human-made wormhole, but not a physically real one. Instead, a holographic wormhole created through quantum computing. Traditional computers operate with bits as their basic unit, which can only exist in one of two states, 0 or 1 at any given time. However, quantum computers use qubits as their basic unit, which can exist in both states simultaneously, known as superposition, allowing for quantum entanglement. Quantum computers are naturally suited to simulate a wormhole, and the task was entrusted to Google's quantum computer, Sycamore. According to calculations based on general relativity, if a massive object passes through a wormhole, its gravity would cause the wormhole to close immediately. To keep the wormhole open, negative energy or negative mass must be introduced to counteract the force of the collapse. While creating antimatter in the real world is difficult, in quantum systems it is relatively easy to manipulate the electric field and change the spin direction of the qubits to simulate negative energy. The first step in creating a simulated wormhole required modeling two black holes, which was the task of Alex Slokapa, a genius programmer from MIT. At first, Slokapa created a neural network with 210 qubits to simulate the black holes, but even Sycamore could not handle a network of that size. It took Slokapa a year to simplify the network down to just 7 qubits, likely the smallest black hole ever created. The first set of 7 entangled qubits served as the entrance to the wormhole, and the second set of 7 served as the exit. 2 additional qubits completed the entanglement, with one serving as the detector and the other as the reference. The detector replaced one particle in the entrance qubits to form a new entanglement with the other 6 particles, while the reference replaced one particle in the exit qubits to form a new entanglement with the other 6 particles. The electric field was then reversed to generate negative energy and keep the wormhole open. Scientists sent information to the entrance qubits, which were then evenly distributed among the 7 entangled qubits like ink dropped into water. When the information passed through the wormhole and was received by the exit qubits, the reference qubit sent back data, and the information was collected back into one location like rewinding time. The experiment was a success, creating the first human-made holographic wormhole in history. To expedite the program, I simplified many of the processes. In fact, this experiment was not easy at all. Scientists spent 2 years conducting countless experiments before finally achieving the expected results. Now let's go back to 1983 and talk about the nature of the universe. Wheeler, who was still teaching at Princeton University, recalled a story involving him and Einstein. He said that after Einstein published the EPR paper, he was very depressed for a long time. Quantum entanglement could mean that our world is uncertain and may change due to the observer. Einstein once asked, "If we don't look up at the moon, does that mean the moon is not in the sky?" Although Einstein did not believe that the world could be subjective, Wheeler believed that the world could indeed be subjective. This is Wheeler's famous theory, participatory universe. In short, If there is no intelligence, the universe does not exist. For example, scientists believe that there have been 10.8 billion humans on Earth, but how many of them can we remember? Apart from those recorded in history books, we do not know who 99% of humans were. In other words, can we consider things that are not recorded as non-existent? Wheeler believed that the essence of the universe may be information. Some people may think this is nonsense. We are tangible entities that can eat several bowls of noodles in one meal. But let's change our thinking. We eat to stay alive, but what is the purpose of staying alive? Perhaps it is to preserve information. The most basic property of quantum is the transmission of information. Entangled quantum particles can represent any form between 0 and 1, so they can store massive amounts of information. Quantum entanglement can also transcend the properties of time and space. From this perspective, the quantum is the carrier of information. Because of the limitation of the speed of light, living organisms may not be able to traverse the universe. However, the information is different. Information has no mass, and when it passes through a black hole, a wormhole will not collapse. Based on the first artificial holographic wormhole experiment, we have reason to believe that parallel universes can be connected through wormholes. This is a remarkable experiment with significant implications. Scientists estimate that there are 100 million black holes in the Milky Way, and these black holes may be doorways in space and time. No one knows what is behind a black hole. Theoretically, if we can fly a spaceship near a black hole and transmit radio waves toward it, the other end of the wormhole will receive our signal. We should be grateful that we were born in this era. We can save ourselves through digital photos, audio, and video. In the future, this information may be transmitted to other universes through wormholes. This idea comes from Wheeler. The essence of the universe is information. Wheeler's life was ordinary but extraordinary. He worked with Bohr and jointly revealed the mechanism of nuclear fission in 1942, which is the basic principle of atomic energy. Wheeler was also the main designer of America's first hydrogen bomb. As an educator, Wheeler trained several generations of American physicists. He supervised up to 50 doctoral students, and many of the authorities in American cosmology and astrophysical theory are Wheeler's students. Throughout his life, Wheeler's fame was far less than that of his collaborator Bohr, his colleague Einstein, or even his student Feynman. However, all scientists agree that Wheeler is remarkable because he was a philosopher and a prophet who could use phenomena to think about the essence of problems. Wheeler's story tells us that not only those who can prove results are great, but also those who can propose forward-thinking scientific hypotheses are equally worthy of the title of greatness. In conclusion, Wheeler's participatory universe theory suggests that the universe may be subjective and that intelligence is essential for its existence. Information is the essence of the universe and quantum is its carrier. The potential of wormholes to connect parallel universes is groundbreaking, and the ability to preserve information through digital means is crucial for the future. Wheeler's legacy reminds us that scientific greatness is not just about tangible achievements, but also about the ability to think beyond them.